So, in today's lecture, we begin our journey towards what's known as the singular value decomposition of a matrix. This notion is widely used by data scientists, and it's probably the perfect note to end the semester on. But in order to get to this, we need to first understand eigenvalues and eigenvalue decompositions of a matrix. So I'll be following string 6.1, 6.2, and 6.4, his Introduction to Linear Algebra textbook, for today's notes. All right, so we will focus on square matrices. So throughout A is going to be a n by n square matrix. Okay. And the question that we are seeking to answer are the question, so what vectors x lie in the same direction as AX? By same direction, I mean plus or minus. So you can reverse the direction, but that's still fine, right? So writing this as an equation, more specifically, we're going to be concerned about which x's and lambdas, so lambdas are just some real number, or no, some number, possibly imaginary, which we'll get to. Which x's and lambdas satisfy AX equal to lambda x. Okay. In other words, what vectors x does what vectors x, when multiplied by A, does the matrix A act like a scalar? And what are those scalars? Right. So I think the best example to start with is the permutation matrix. So let's kind of play around with this without writing down any specific formulas to compute this, which there are. Let's just think about it conceptually. So let's let A be the permutation matrix 0, 1, 1, 0. Okay. So what vectors x, when we multiply by A, are going to be in the same direction? So you should probably understand what I mean by permutation. So let me talk about that first. So if this is our matrix 0, 1, 1, 0, and we multiply x1, x2, what's going to be the output? It's x1 times this column plus x2 times that column. So what's the output?
x1, x2.
x2, x1, right? Because it's x1, so it's like x1 times 0, 1 plus x2 times 1, 0. So by permutation matrix, I mean it's just going to swap the x1 and the x2, right? You see that?
Yeah.
So when considering now that we understand that this just swaps the entries, I'll just tell you right ahead that one lambda is going to be, one of them is 1. So what vector is equal to, what vector satisfies this equation? And remember, this is just swapping the entries. So give me some numerical values to put there that'll satisfy this equation.
You could do like 5, 2, 2, 5.
So if this was a 5 and 2, you would have 2, 5, right? But we want this. That's what we want. We want the same x on the output. This x.
Oh.
So what's another choice?
The values for x would have to be equal.
Right. So you do
like 0, 0 or.
Well, for now we're going to exclude. We're going to exclude x equals 0. That vector is not really interesting, but this will work here, right? So for this eigenvalue, a corresponding eigenvector would be 1, 1. Okay. But as you mentioned, in fact, anytime that these numbers are the same, that's also going to work, right? Like if that was a 4 and a 4, it would still work, right? In fact, any multiple of this vector is also an eigenvector. And so any multiple of this vector is also an eigenvector. Okay. So, all right, this is good. We found an eigenvalue and we found a corresponding eigenvector. Next, I'm going to tell you a fact that the sum of the eigenvalues is equal to the trace of the matrix. And what do I mean by trace? The trace of A is just equal to A1, 1 plus A2, 2 plus 1.5 plus A and N. So what's the trace of this matrix here?
Zero.
0, right? So the trace of this matrix is just 0. And we know that one of the eigenvalues is 1. We're hoping that there might be another one. What do you think the value of the other eigenvalue is? If the sum of the eigenvalues equals the trace, what is the other eigenvalue for this matrix?
-1.
-1. Perfect. So that has to be the other eigenvalue. Now, okay, so now the question becomes, for the permutation matrix 0, 1, 1, 0, what vector is going to satisfy this equation? Right, and this is, again, that's x and that's x.
Is it just going to be 0, 0, or are we still excluding that?
Yeah, we were still excluding the 0 vector.
Okay.
-1, -1.
Well, then if you had -1, -1, then this multiplication would just be -1, -1, but then multiply that by -1, you'd have 1, 1. So then you wouldn't get
So 1, 1 again.
1, 1. Well, again, if you plug that in, that times that is just 1, 1. But now we have -1, -1. That's not the same vector.
Gotcha.
Yeah, it's a little tricky at first, and I admit, but it's just, it takes a little bit of thinking, right? What about this one? What about 1 minus 1? Right? What does that product equal? That product equals what? -1, 1, right? But this is equal to -1 times, make sure you can still see that, 1 minus 1. So did that work? Here's x, there's x, and there's lambda. You see that? Make sure you can. So do you see that this vector works? It satisfies that equation, right? Ax equals -1 times x.
Yeah, that makes sense.
All right, so 1 minus 1 is an eigenvector. Corresponding to lambda 2 equals to -1. Can someone give me another eigenvector corresponding to that eigenvalue?
Just any multiple of it? Like, I don't know, like 2, -2? Or are
Yeah,
you looking for something else?
that'll work. That'll work for sure. What about -1, 1? Will that work? Yeah, right? This will be -1 times -1, 1. Right? And that's because this was a multiple of that, right? -1 times that is that. So any multiple of it. Okay, so all right, these are the eigenvalues of this matrix. Now, what's nice here is that we had no repeated eigenvalues. When there are repeating eigenvalues, we don't necessarily get good eigenvectors. And by that I mean we don't get n eigenvectors. Our hope is, I'll just say, like, I'll just put a star next to this. We hope to get n in linearly independent eigenvectors. For a square n by n matrix. That's our hope. And by that, I mean that when we were doing like -1, 1, -2, 1, -2, 2, -3, 3, those are all multiples of the same eigenvector. But this vector here is linearly independent from this vector here. So we got it in this case, and we're happy. And it happened to be because this matrix is symmetric, and we'll get to that later in this lecture. So, okay. How to solve this now, right? In general. How can we do that? And again, we're not necessarily interested at all in the zero vector. Okay. So we want, what do we want? So we want AX equal to lambda x. We want to find those x's and lambdas. Okay. All right, so maybe if we subtract on both sides, so that's like saying we want AX minus lambda x to equal to zero vector, right? But okay, we can factor out x and write this as A minus the identity matrix times lambda x equals 0. And again, we are assuming that we don't want the zero vector. Okay. Now, so on that note, right? Because we don't want the zero vector, if A minus I times lambda, so the identity matrix, if that was invertible, then we could just multiply both sides of this matrix by the inverse. Again, lambda is a scalar times the identity matrix, right? And the inverse times 0 is just 0, right? But this inverse times that is just the identity. Oh, identity times x is just x. Oh, bad. So if that matrix was invertible, then the solution that we get is x equals to 0. So that means that it's not invertible, right? We don't want it to be invertible. It means that this right here, this matrix must be what we learned is called singular. Right? It's not invertible, it's singular, which means, which we learned last time, is that the determinant of this matrix, well, running out of room, singular means that the determinant is 0. And we know how to find the determinant, more or less. We can use row operations to reduce this matrix to an upper triangular matrix, and then we take the product of the diagonals. That's one way to do it. But this gives us at least a method for computing these eigenvalues and eigenvectors. We need to figure out what lambdas make this work, right? So maybe we should use an example just to see. So let's take A equal to, I don't know, 4, 1, 1, 4. Okay. And then I times lambda in this case is just going to be lambda 1, 0, 0, lambda 2. Right? Just not lambda 1, lambda 2, just lambda, lambda. right? Lambda times the 1 in there, 0, 0, and then lambda times that 1, right? Lambda times the identity. So then A minus I lambda is just equal to the matrix 4 minus lambda 1, 1, 4 minus lambda. Okay. So now let's take the determinant and set it equal to 0. So it's bar meaning determinant. So in the 2 by 2 case, this is easy, right? It's A times D minus C times D. Right? That times that minus that times that, which gives us 4 minus lambda squared minus 1 is equal to 0. So, which gives us 16 minus 8 lambda plus lambda squared minus 1 is equal to 0. Which means that lambda squared minus 8 lambda plus 15 is equal to 0. And we solve this polynomial for lambda. Okay. So we can factor this as lambda minus 3, lambda minus 5 is equal to 0. And we get that the eigenvalues are 3 and 5. Those are the solutions to this polynomial. Okay. So now that we know the eigenvalues, we can next figure out eigenvectors, right? So choosing lambda equal to 3, we know that the determinant of 4 minus 3, so 1, 1, 1, and 4 minus 3, 1. We know that, not the determinant, sorry. We know that this matrix is now singular, right? Because A minus I times lambda is always singular. So in other words, we need to figure out, it's just important to note, but we know that, what do we know? We know that equation, right? I need to keep it up here somewhere. We know that the eigenvectors satisfy this equation, which is this one, right? So what is a solution here? We can just look at it and guess one. What is a solution? Super easy. Come on, guys. A solution here is simple. Just pick an x1 and x2 to make it the zero vector.
One and negative one?
Yeah. 1 minus 1. Good. Right? 1 times that column plus negative 1 of that column is 0. So what about with the other lambda? So then we have 4 minus 5, so minus 1, 1, 1, and 4 minus 5 is another minus 1. What's another eigenvector?
One and one.
Yeah. One and one. So these are eigenvectors corresponding to these eigenvalues. But also any multiples of these would also be eigenvectors, right? But these happen to be linearly independent from each other. In fact, this is a very important note. Back to this question here, we hope to get n linearly independent eigenvectors. I'll keep this on the board for the rest of the lecture. The distinct lambdas correspond to linearly independent eigenvectors. That's an important note. That's going to be linearly independent from that because they have different eigenvalues. Okay. So it's important to also note that we could have actually found out these eigenvectors and eigenvalues before, without doing all these computations. Why?
Sorry, I'm sorry. I just wanted to ask really quick. You could have also chosen -1 and 1 for the first
Yes.
eigenvector,
Yeah,
right?
any multiple of this one. So
Oh, it's a multiple. Okay, gotcha. Yeah. So there's still only two, not three. Okay.
yeah, good point though. Good point to like emphasize that by questioning it. So we learned with the first example that this matrix had eigenvalues. What were they? What was it? 1 and -1, right? And the corresponding eigenvector, the 1 was 1, 1. And then we also had lambda 2 equals to -1. And for that eigenvector, for an eigenvalue, it was -1, 1. And what was the matrix that we started off here with? We started off with 4, 1, 1, 4. Notice the eigenvectors. Right? They're the same. Right? They're the same for these two matrices. Well, why is that? Well, we should probably make note that, so let me just go ahead and write down, I'm going to use this spacer here. So let me write down the eigenvectors and values, 3 and 5. And they have the same eigenvectors, but the eigenvalues changed. Okay, so why is that? So to answer the question why they have the same eigenvectors, but different eigenvalues, what are the eigenvalues for the identity matrix? What are the eigenvectors? I mean, what are the eigenvectors for the identity matrix? They're all so if I choose a lambda there, that's going to be, well, okay, let me start with a more basic equation. I think I might have confused you with that. We know that the identity times x is equal to x, right? So we know that lambda times I x is equal to lambda x, right? So if we just think of, if we multiply alpha times I x, it's going to be equal to alpha times x for any choice of x. So for the identity matrix, every vector is a eigenvector, right? And any multiple of I, that multiple will be an eigenvalue for any given x, for any x. Does that make sense? Like any multiple of I, that multiple is an eigenvalue, right? Because this holds, which means that if I multiply by anything, it's going to be the same, and that value that I multiplied will be an eigenvalue. Again, it doesn't. I don't have to use lambda. Lambda, I can use any scalar. But yeah, I'll just leave it lambda. If lambda is a multiple of I, lambda is an eigenvector of that matrix that you make. So here, right, that matrix right there. Well, I'll just give it a name A for general. Like that's A. So A x, so we're assuming x is an eigenvector. Assume x is an eigenvector, so of A. And then alpha times I x, x is still going to be, it's an eigenvector of A. Well, this is going to be equal, so AX is going to be equal to lambda x. And alpha x is going to be equal to, well, I'm going to use plus. So alpha IX is just alpha x. So factoring out x on the left-hand side, we see that A plus alpha times IX is equal to lambda plus alpha times x. So if x was an eigenvector of A, then x is an eigenvector of A plus alpha times I, right? And the new eigenvalue is lambda plus alpha. So what is this matrix here? This is just 0, 1, 1, 0, plus 4 times the identity 1, 0, 0, 1. That matrix is just this, which means that it's got to satisfy this equation here. And because this is just the identity, so the identity is special in that every vector is an eigenvector of the identity. So this matrix can share eigenvectors with this one, so we put them into that equation, and we see that, oh, what are the eigenvalues of the resulting matrix? Well, alpha in this case, we chose to be 4, so the eigenvalues are going to be 1 plus 4, which gave us that 5, and then negative 1 plus 4, which gave us that 3. And the eigenvectors are the same. The eigenvectors of A are the same as the eigenvectors of A plus any multiple of I. So that was like another way that we could have found these eigenvalues and known the eigenvectors. But in general, this is only for the identity matrix. In general, it's important to note that for a matrix B, That's not going to hold, right? Because A and B in general will have different eigenvectors. So you cannot use linearity for two general matrices. You only can do that when you have the identity, because the identity shares eigenvectors with every other matrix. Okay, so that's just an important thing to note. Okay. So now to some bad news. And to illustrate the bad news, I'll say let R equal, what is it? Forget the, is it negative cosine? It's cosine. I think that's the right intuition there. Yeah, that's it. R, where this is the rotation by angle theta matrix. All right, so what do I mean rotation by angle theta? Let's choose theta to be 90 degrees. Okay, so then what does R become? So cosine of 90 is 0, sine of 90 is 1, negative cosine of 90 is 0, and then, did I write that down right? Oh, I knew I wrote it down wrong. Yeah, I was like, something was off. It's rotation, I need to remember that. So this would be negative sine of theta, cosine of theta. Sorry, okay. So that means that this entry would be -1, and then cosine of 90 again is 0. So what do I mean by rotation? Well, let's look at the matrix, I mean the vector 1, 2. There's a vector 1, 2. And if we multiply it by this matrix, what happens? Well, 1 times that column, so 0, 1, plus 2 times -1, 0. So what do we get? -2, 1. So -2, 1. There's the resulting vector after matrix multiplication, and we have rotated that vector by 90 degrees. So that's why it's called a rotation matrix. All right, so do we understand what the rotation matrix does? It takes an input vector and outputs a vector at a 90-degree angle to it. So if that's R, right? What lambdas and x could satisfy that? Does that have any solutions? just geometrically, what does it mean for this to happen? The matrix times the vector is a scalar multiple of the vector. Can that happen with the rotation matrix here at 90 degrees? What does a scalar times a vector do? It just stretches it or reverses it, right? That's all a scalar multiple does. So can this matrix times x ever stretch a vector or reverse it? Anybody?
No, since it's always just rotating it.
Right. For what we would expect is to be either that way or that way, right? But if it's always going to rotate it, it can never be on that same line. So let's try to compute for this matrix here. Let's try to compute the eigenvalues and see what happens. So as before, we set the determinant equal to 0. So 0 minus lambda minus 1, 1, 0, I know, 0 minus lambda, or just minus lambda. Oh, I'll write it there. So we set that equal to 0, which means that times that minus that times that. So we get lambda squared minus 1 is equal to 0, which means that lambda squared plus 1 is equal to 0. Oh, that means that lambda is equal to plus minus square root of -1. And this is just equal to I, right? Plus or minus I. That's the bad news. There are no real eigenvalues for this rotation matrix. Okay, so that's the bad news. Eigenvalues may not always be real. And that's because, again, this is rotating a vector and it will never land on itself ever, unless x is equal to 0 or lambdas are imaginary. Okay. All right, so, all right. Now, okay. That's pretty much all the bad news is that you have to worry about this, and then sometimes you might have repeating eigenvalues. Those are the bad news. All right. So now we make it to the important stuff. Okay. In fact, I'll go ahead and write this here as another important point before we get to that other important point. Symmetric. Actually, I'll include it with this. Actually, it goes with this other bullet here. Symmetric matrices have real eigenvalues. So those are good ones. So if the matrix is symmetric, recall symmetric means A equals A transpose. Those have real eigenvalues, so that's really good. Okay. So here is the big thing for today's lecture. To make sure I'm not skipping over anything. Yeah, all right. Here is the big thing. So eigenvalue decomposition. Otherwise known as diagonalizing a matrix. So our goal is going to be to factor a n by n matrix. And how are we going to do that? Suppose, what am I going to suppose? Suppose A has n linearly independent eigenvalues. And put these in the columns of a matrix X. Okay, now note that if these are n linearly independent eigenvectors, I don't know why I wrote values. Eigenvectors. Since these are linearly independent, note that X is invertible. Right? When you have if the columns of the matrix are all linearly independent and they're square, you can invert the thing. So X is invertible. Right? Now, okay, so next, let's look at A times X. Okay, so what does this look like? This is like A times I'll have to use subscripts maybe. Yeah. X1, dot, dot, dot. So these are columns. So these are the n linearly independent eigenvectors of A. If you have n linearly independent eigenvectors, you have n distinct eigenvalues. So the resulting matrix here. So how do we build the columns of the resulting matrix? Well, it's like A times X1, dot, 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 A times Xn, right? Like that. But these are eigenvectors. So we know that A times X1 is going to be equal to lambda 1 times X1 because they're eigenvectors. Okay. So A times X is equal to the lambda 1s times the lambda i's times the vector xi, where xi is a eigenvector. So now this is actually a very easy matrix to write as a product. We can write this as lambda 1, lambda 2, dot, 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 and n. This diagonal matrix, where there's zeros all over the place, the only values are on the diagonal. It's like, okay, times x1 column, dot, dot, xn column. Right? X1 times here will give us there. That column times the next ones, so forth and so on. you see that this works out. So I'm going to call this diagonal matrix, if the lambda is on the diagonal, I'm going to call that capital lambda. And then this is just x again. So what do I have overall? I have that ax is equal to capital lambda x, which would make sense, right? A little x is equal to little lambda x, and we just put them all in matrix form. Oh, yeah, this should make sense. Okay. No, wait a minute. Something's off. What is off? Oh, I see what's off. This, y'all should have caught me on that. This matrix product would not work out. It's the other direction here. It's x1 dot xn n times the diagonal matrix. Yeah, something is definitely off with that. Lambda 1, lambda 2 dot lambda n, and then zeros everywhere else. So this would be x times lambda. Now, yeah, now it works. Now it works. Yeah, because it's lambda 1 times x1 plus 0 times every other column will give me the first, will give me that. And then 0 times x1, lambda 2 times x2, 0 times all the other columns will give me this, that column there. All right, works. So ax is equal to x lambda. All right. So, but we know that x is invertible, right? X is invertible, which means that I can multiply both sides of this equation by the inverse of x. Oh, x times x inverse, we're just left with a. So a is equal to x lambda x inverse. That's an eigenvalue decomposition of A. It's a factorization of A. You can factor A into, we have eigenvalues, we have eigenvectors as the columns of this matrix. On the diagonal of this matrix, we have the eigenvalues, and then we have the inverse of x. Okay. So, noting that so when can we do this? Well, A has to have n linearly independent eigenvectors. If that's the case, then we can always factor A. And what am I going to note now? My white. Oh, it's right there. Symmetric matrices can have this property. So if the matrix is symmetric, then it has n linearly independent eigenvalues, which are real. So if the matrix is symmetric, it has n linearly independent Why do I keep on writing values? So annoying. Eigenvectors. In linearly independent eigenvectors, which can be chosen to be orthonormal. What does that mean? Orthonormal. That's going to be a very important notion, but at the very least, before I get into orthonormal, symmetric implies in linearly independent eigenvectors, which means every symmetric matrix A will have this decomposition. That's the important point. Every symmetric matrix will have real eigenvalues and also this decomposition of eigenvectors, eigenvalues, inverse of the eigenvector matrix. Okay, that's the important point. Now, getting to the more specific point, the big points that we're getting to. The orthonormal. What does it mean that we can also choose the vectors to be orthonormal? So, definition, vectors v1 through vn are orthonormal if vi transpose times vj is equal to 0 if I is not equal to j. And let me make sure, what notation does your textbook adopt? One second, let me make sure that I'm not using anything that's outside your textbook. Hold on. No, they use Q, I use V, whatever. Textbook uses vectors Q. I get it. So I should have used Q, but Strang likes Q. In fact, a lot of textbooks like Q's to represent orthonormal vectors, or collections of orthonormal vectors. So what does this mean? It means that the dot product between two vectors is 0 when they're orthogonal to each other, right? They're perpendicular. So it's in layman's terms, I should say this is a collection of pairwise perpendicular vectors, each with unit length. That's what a collection of orthonormal vectors is. Oh, that should be a 1. Okay, so hopefully that makes sense. This is a collection of pairwise perpendicular vectors. So for example, this collection, that is a collection of orthonormal vectors. These are orthogonal, they're right angles to each other, their inner product is 0, and they both have unit length. So that's an example of a collection of orthonormal vectors. Okay, so we need another definition now. I hate to erase that, but we're gonna have to. So Q is called orthogonal if the columns of Q are orthonormal. You see that? Yeah. Okay. We have two major definitions here. A collection of orthonormal vectors and then an orthogonal matrix. So a very important fact about orthogonal matrices, so fact. Q transpose is equal to Q inverse. Q transpose is equal to Q inverse. Why is that? Well, let's test it out. What's Q transpose times Q? Well, that's the first column of Q as the first row of Q transpose. The second column is the second row, so forth and so on, to the nth column. And then we have Q1, Q2, dot, 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 Qn, like this. Okay. So what is this product going to be? What is this product going to be? How do we get the first column here? Right? How do we get, not even that, how do we get the first entry right there? The first entry is Q1 transpose times Q1. That gives you the very first numerical entry right there. And we know that's going to be a 1. How do we get the second entry? It's going to be Q2 transpose times Q1. Well, these are orthogonal. They're perpendicular, which means that the inner product between them is going to be 0. And that follows all the way through to the last one, that times that, which is 0, because they are perpendicular. They're orthonormal. How do we get this entry? The 1, 2 entry. Well, it's Q2 times Q1. They're orthogonal, so that's 0. How do we get that entry? Well, that's Q2 times Q2. They're unit vectors, so that's just 1. 0's all over the place. We get the identity. Okay. This is what's so special about orthonormal matrices. That the transpose is equal to the inverse. And you can verify that Q times Q transpose on your own is also the identity. All right, we're almost there.
So this only works with square matrices, yeah?
Correct.
Okay.
Yeah, when I wrote at the beginning that I should have left it up there that every matrix that we're considering right now is square.
Gotcha. Okay.
Okay. All right, so let A be symmetric. So if asymmetric implies that A is equal to X lambda X inverse. Right, that was the big factorization, right? Okay. Now, since it's symmetric, we were going to be able to pick the eigenvectors to be orthonormal. So we can make that matrix Q, X, we can make that into a Q, an orthonormal matrix. Eigenvectors orthonormal. So we can get this orthogonal matrix. So eigenvectors orthonormal imply X orthogonal. Which means that we can write A as, let me use the same, they use Q's as well, so I'll use Q's. Q lambda Q inverse, which means that A is equal to Q lambda Q transpose. That's the big thing. Q lambda Q transpose. That's what A can be factored into. Okay. Now this is an especially nice matrix now. This is an especially nice factorization because the columns of Q are all orthogonal to each other. They have unit length. This is a diagonal matrix. And this is what was I going to say? I was going to say unit length columns and rows. Okay. So that's good. We like it when A is symmetric because now we have a nice factorization. And why would this be useful? Why would this be useful? Well, this is useful because this matrix A can be very, very expensive to store. It can be very dense. Whereas these matrices here are sparse. The columns here, the rows, they all have unit length, and this is a diagonal matrix. So this could be a very large, expensive matrix to store. Where here, most of the entries in all of these matrices are zeros, right? Most of them are zeros. So this is an n by n matrix with only n entries in it, right? And these have unit length. The storage requirements now are you take this large matrix A, and if it's symmetric, you can factor it, and it becomes 3 relatively light matrices to store in a computer. Okay. So that's good. That's nice. But now, what about, maybe, where's my way? What about non-symmetric matrices? What about even, non-square matrices, n by n A? We could never hope to find this type of decomposition for a non-symmetric, much less a non-square matrix, could we? Well, sadly, like, there's nothing that we can do as far as eigenvalue decompositions for a general matrix A. But like, can we get around it somehow? Well, so if A is m by n, how big is A transpose times A? What's the size of that matrix? So this is what? N by m, and then A is m by n. So what is the output going to be?
N by n.
N by n. Ah, so wait a minute. It's squared. Okay. What about, what's A transpose times A transpose? We did this formula once. Do you remember? Like, remember that I wrote this down at one point. A times B transpose is B transpose times A transpose. That's just a fact. So what is this going to be? This is going to be A transpose times, so it's this transpose times that transpose. The transpose of a transpose is just itself, right? Wait a minute. A transpose times A all transpose is equal to A transpose times A. This is symmetric. A transpose times A is a symmetric matrix. A times A transpose is also symmetric. Right? But in particular, A transpose times A is a square symmetric matrix. And this is where we get to the big thing. The big thing. I wasn't expecting to get to it, but we did. A transpose times A. It's symmetric, square symmetric matrix. So we know that we have this eigenvalue decomposition with orthonormal eigenvectors. So, we know that, I'm not going to use the notation yet, but we know that it has this decomposition. We know that it has that decomposition. Okay. So this is like close, right? For a general n by n matrix. We can do that because this is symmetric, and we know that if it's symmetric, we can have orthonormal eigenvectors, and we get this nice nice little factorization. So let me look ahead a little bit. I think actually this is a perfect place to stop. This is a perfect place to stop. Right here, because this is right before the big thing. The big thing being, so next time, the singular value decomposition. Also known as the SVD. Okay, so we'll stop here and let me. I know I said I wasn't going to do it, but this is like super important stuff. This is from Strang. So 6.1, 1 through 6. I had other ones. And then 6.2, 1 through 4. And again, just turn it in by Friday or Saturday. Saturday's fine. Okay. Tomorrow we make it to SVD, and I'm pretty excited about that because you probably are wondering why in the world are we factoring. Trust me, you'll see tomorrow.